The greatest of human endeavors is a risky business.
Yes, we've had a problem here.
NASA led the world into the exploration of space, but behind the scenes, out of the public eye, mistakes, mishaps, and failures plague the space industry.
Obviously a major malfunction.
Discover how NASA space failures further exploration. NASA's space shuttle program ended in 2011, and NASA is now focused on placing humans on Mars. To achieve that goal, NASA is designing the Orion spacecraft, which will take humans deeper into space than ever before. NASA is building on the success of the space shuttle, and more importantly, learning from their mistakes. 2006. 3 years after Space Shuttle Columbia broke apart while returning to Earth from the International Space Station, NASA prepares to launch a shuttle for just the second time since the accident. The first return to flight mission a year earlier was a resounding success. Now, if all goes well with this mission, the Space Shuttle program will be cleared to return to full operational status with numerous Space Shuttle missions once again scheduled each year. Perfection is not possible, but NASA knows how important the mission is and needs it to be as flawless as possible. July 4th, 2006, American Independence Day. A fitting metaphor for today's launch. Led by veteran Commander Stephen Lindsay and pilot Mark Kelly, a crew of 7 astronauts are set to rip through Earth's atmosphere en route to the International Space Station.
America is ready to return the space shuttle to flight, so good luck and Godspeed, Discovery.
I can't think of a better place to be here on the 4th of July on the Independence Day to be getting ready to launch into space.
Kennedy Space Center buzzes with nervous excitement. Launch control is tense, but unknown to the spectators, media, and dignitaries in attendance, an event is about to send shock waves through NASA's flight team and drive tension in launch control to new heights.
9, 8, 7, 6. Go for main engine start. Main engine start. 2, 1. Booster ignition and liftoff of the Space Shuttle Discovery, returning to the space station, paving the way for future missions beyond.
Powered by 2 solid rocket boosters and 5.6 million pounds of thrust, Space Shuttle Discovery streaks through the atmosphere at rapidly increasing speeds. Hundreds of systems are monitored by launch control engineers. Then, just 22 seconds into ascent, readings from a pressure transducer literally go off the charts.
Carl, what we got?
Looks like we got an overpressurization condition on the FRCS.
Engineers watch helplessly for the next 60 seconds as the pressure hits levels never before seen, then shockingly goes even higher. So high that the pressure transducer can no longer measure the pressure. The problem is in the forward section of Discovery, in front of the crew module, where the astronauts are. The shuttle is already traveling over 1,000 miles per hour. In another 60 seconds, it will reach 3,000 miles per hour. A few minutes later, 18,000 miles per hour, 9 times faster than a rifle's bullet. Nothing can be done until Discovery makes orbit. But 1 minute and 14 seconds into ascent, the pressure transducer starts recording the pressure again, and it begins to fall. Within another 60 seconds, the readings are within normal range again. Engineers are relieved for the moment. All other flight readings seem to be normal.
Standing by for solid rocket booster separation.
Discovery reaches orbit with no other issues. The crew begins their mission duties, which primarily involve testing new safety and repair procedures designed from what NASA learned from the Columbia accident. Back at Launch Control, questions about the massive pressure buildup grow. NASA has never seen this problem before, and engineers initially question whether the pressure transducer is bad and giving false readings.
Could be an instrumentation problem.
Yeah, that's true. We'll have to do a data retrieval and see what we've got.
Okay.
We'll put that in work.
If it's working properly and the pressure was real, then the lives of the astronauts could still be in danger. Chris Curtis is the orbiter subsystem manager. He's assigned to head up an investigation team.
During ascent, you've got air trying to escape out of the FRCS on ascent, running back through the vent doors. Air's trying to move. Basically, it's like a balloon trying to pop.
The FRCS is the Forward Reaction Control System. It contains many of the primary thrusters used to maneuver Discovery while it's in space. It's full of tanks of toxic, highly explosive rocket fuel. Mark Mansfield, a structures analyst, is concerned that the pressure could have bent or warped Discovery inside the FRCS.
As you load up these parts with pressure, you could get to the point where you could break some piece of hardware or break a skin panel, do something that could be detrimental to the mission or catastrophic.
When NASA says catastrophic, they mean Discovery could be destroyed while returning to Earth. This mission is the second test flight after the loss of Columbia. Success and NASA would return to a full flight schedule. A failure would mean the immediate end of the Space Shuttle program.
Find out the root cause of the problem and see if we can get safe.
NASA needs answers, and fast. While the crew of Discovery tests new safety and repair techniques required after the loss of Columbia and resupplies the International Space Station, NASA's investigation team works feverishly on the ground.
If we do have a real problem, then we have to concern ourselves with the overpressurization of the FRCS cavity and the loads exerted on the bulkhead, and that would result in some stresses to some of the struts and the associated bolts.
They only have 13 days to decide if Discovery is safe to return. If not, then NASA will have to scramble a never-before-attempted rescue mission.
We laid out basically an investigation process of what do we do to get comfortable to land the vehicle.
The pressure transducer is the first suspect.
Nalena, do we have a real problem? Is this data real?
Well, there doesn't seem to be a problem with the instrumentation. The data does seem to be real. It doesn't seem like there's a problem with the transducer itself.
It is remotely tested and seems to be working fine. But the transducer cannot be fully tested while in space, and so the team cannot conclusively eliminate a faulty transducer until Discovery returns. For the safety of the crew, they must presume the pressure was real. Comparing the pressure readings to the averages of previous launches reveals that the peak pressure was at least 3 and possibly 4 times the normal reading, and because the pressure went off scale, engineers cannot immediately determine how bad the pressure might be, making it difficult to know how much damage might have occurred to Discovery. As the shuttle ascends and air inside the forward reaction control system expands, it is normally released through 2 vent ports in the bulkhead. The only way the pressure could be real is if not just one, but both vent ports were blocked at the same time.
It would take both ports to be blocked to get this type of pressure change. So we're thinking, what potentially could happen is it, the probable to block both ports?
Because of the design of the forward reaction control system, the likelihood that both vent ports could be blocked simultaneously seemed almost impossible. While the team was becoming more convinced that the pressure transducer or some related instrumentation must not be working properly, they still had to assume that the pressures were real, or risk Discovery being destroyed in re-entry along with the entire crew.
Do we need to do any type of testing while they're on orbit to see what real margins are? I mean, analysis is one thing, but...
What we have to do is go back and look at the certification analysis and see what loads we've analyzed for, and then come back and look at what our overpressure condition is, go back and redo the analysis for the new overpressure condition, come up with a new margin.
Days are spent exhaustively extrapolating the pressure readings to estimate a maximum pressure differential, a worst-case scenario. How would the worst possible pressure affect Discovery? Would there be damage? If so, how much?
The result of the analysis showed that we were close. We went and did some testing. Testing showed that we were in good shape, and based on the results of both analysis and tests, we said we were okay to come back.
NASA gives the okay for Discovery to return based on solid scientific analysis. But any unexplained anomaly haunts engineers until the spacecraft and crew are all safely on the ground. Mission Control monitors the pressure transducer carefully during the 30-minute descent through the atmosphere. All readings are normal, and Discovery lands without incident.
Make a touchdown.
As soon as Discovery is safely in the orbiter processing facility, engineers fully test the pressure transducer, hoping to finally resolve the mystery. They are dismayed when it is conclusively proven that the pressure transducer is working perfectly. The pressure during launch was real. The team will soon discover the shocking truth behind the massive pressure buildup during the critical July 4, 2006 launch of Space Shuttle Discovery. The massive pressure recorded 22 seconds in the launch of Space Shuttle Discovery was almost 4 times the normal pressure. With proof that the pressure transducer was working correctly, NASA is faced with a growing mystery. A mystery that must be resolved before the Space Shuttle program can be cleared to return to a regular flight schedule. NASA orders the micro-inspection team to inspect the vent ports to determine if anything is blocking the ports. A tiny camera system called a borescope is inserted through the ports, enabling the team to see the inside of the vent all the way into the FRCS. Both vents are inspected, but the vents are clear. No obstructions or debris is found. Nothing is blocking the ports, and no other evidence is found to help solve the mystery. Everything in the vent ports looks perfect. Dismayed, the team pores over engineering and design schematics for answers. Near the vent ports, TCS blankets, or thermal control system blankets, cover many surfaces in the FRCS. TCS blankets protect the spacecraft's surfaces from the extreme heat and cold of space. TCS blankets are located in front of the vent ports on an adjacent wall of the FRCS.
It's just the probability of blankets blocking the ports was very low. I mean, very, very low. It's just never happened in the past. We've never had a problem with the TCS blankets.
Anthony Chambers oversees the thermal control subsystem hardware for Discovery.
The original blanket was installed underneath a PVD drain line, purge vent and drain line. It's about a 1/4 inch diameter stainless steel drain line. And this drain line acts as a billowing limiter for the blanket.
When the blankets are installed correctly, it is impossible for them to block the vent ports. The team reviews closeout inspection photos of the blankets. The last closeout photos of the blankets show that they were installed correctly, so the drain lines, by design, would prevent the blankets from coming near the vent ports. As frustration grows, another borescope inspection is scheduled. But this time, the area is accessed by a topside electrical panel to get a better look. Then, a breakthrough.
We could see that the blanket was installed over the drain line.
Somehow, the blanket is over the drain lines instead of behind. Testing confirmed that without the drain line to hold them back, the blankets could be sucked into the vent ports during ascent, creating the intense buildup of pressure inside the FRCS. And during re-entry and landing, the rush of air into the FRCS would have blown the blankets back into their original positions, which is why the first borescope inspection found nothing blocking the vent ports.
When you're coming back to Earth, you actually have air rushing back into the vehicle, so you're actually pushing the problem back to its original state.
NASA is relieved to finally know what the problem is, and confirms that the forward reaction control system was not damaged by the pressure. But now the investigation team is faced with an even greater mystery. Why are the blankets installed wrong? An extensive investigation reveals that a series of mistakes and mishaps spanning several years resulted in the blankets being installed wrong, which led to the dangerous pressure buildup during launch. The original thermal blankets were installed in 1984 when Discovery was being built. At the time, NASA was designing the space shuttles to fly for only 10 years, or 100 missions, and the blankets were never expected to be removed.
The original installation of the blanket didn't have a slit, an access slit here. It was just a cutout for the bracket, so the blanket went on first. The bracket was installed, the blanket went over the bracket, and then the line was installed. The blanket was trapped underneath that line.
Nearly 20 years later, in 2002, during a series of major modifications to Discovery, the forward reaction control system was removed, and the blankets were removed for the first time to inspect the structure beneath the blankets.
We had to remove this blanket, so we had to cut it out. And when we put it back in, we had to provide a slit line to allow that blanket to slide in around and underneath that bracket.
The new blankets were installed correctly under the drain lines and flew without incident in July of 2005 during Discovery's historic return to flight mission. But when Discovery returned, the FRCS was removed again. Could this have been when the blankets were installed wrong? But why was the FRCS removed? The investigation is about to discover a cascade of mistakes. The forward reaction control system was removed from Discovery after the successful 2005 mission. The pressure buildup happened during the 2006 mission, so something must have happened to the blankets while the FRCS was removed. But why was it removed? The investigation team discovered that a temporary repair that was cleared for the 2005 mission had to be permanently fixed, and it could only be fixed by removing the FRCS.
We were performing the crew cabin leak check. What we noticed is that we had excessive leakage, so we did a lot of troubleshooting trying to figure out where the leak was coming from.
The crew cabin leak check is performed to make sure that the fragile atmosphere inside the spacecraft that keeps the astronauts alive while in space stays inside and does not leak out. Obviously, a critical test, and this time, air was leaking out.
Well, it was narrowed down to what we call a bulkhead feed-through receptacle.
The receptacle permits critical wiring to pass through the bulkhead from the crew cabin to the FRCS and is supposed to completely seal the area so no air escapes from the crew module. Whitcoff's team discovered that the receptacle had not been tightened down enough after a damaged connector pin had been replaced.
We have other receptacles in this area. We believe that possibly the socket may have contacted an adjacent receptacle, and the technician was led to believe he got the proper torque, thus caused the leak path. As you see right now, the FRCS is off. Well, the FRCS was on, and we could not reach this receptacle.
As the 2005 return to flight launch day approached, there was no way to fix the problem. So after extensive analysis and approvals, a high-tech space sealant called RTV, or room temperature vulcanizing sealant, was applied and stopped the leak, but the temporary fix was only approved for one mission.
So we flew STS-114, we came back, and due to this restricted configuration where we had RTV sealing around this receptacle to prevent the leak path, we had to remove the FRCS to replace it.
But the repair of the bulkhead feed-through receptacle did not affect the thermal control system blankets. So when were the blankets installed wrong? Further investigation revealed that when the FRCS was removed from Discovery, it was transported from the orbiter processing facility to the hypergolic maintenance facility because NASA decided to do some maintenance on 2 fuel lines while the FRCS was removed from Discovery. This is when a dangerous mishap occurred that put 2 technicians in a life-threatening situation and finally revealed the answer to the mysterious blanket installation. To maneuver in space, fuel is burned to provide thrust, but without oxygen in space, spacecraft must also carry a chemical called oxidizer in order for the fuel to burn. Fuel is in one tank, and the oxidizer is in another tank. When the two mix, the fuel burns, producing thrust. Both the fuel and the oxidizer used by the space shuttle are lethal to humans. So when any work is performed on the tanks or fuel lines, technicians are required to wear scape suits or self-contained atmospheric protective ensemble. Actual never-before-seen security footage of the repair operation shows the technicians as the deadly oxidizer is accidentally released. When the oxidizer mixes with water vapor, it becomes deadly nitric acid.
It's oxidizer, it's vaporizing like crazy.
Running down on their suits, off their backs. And
it's nasty stuff.
Running down off the spill protection, cleaning up what was spilling as fast as they could.
And there was nothing stopping. There was no way to stop it.
Fought it the best we could till it finally ran out of propellant.
The scape suits had done their job, protecting the technicians.
Reached in with a tool and pulled the filter. And as soon as we pulled it, I guess it broke that vacuum we had on there that was keeping it from coming out, and it just started running out.
When we enter these tanks like we do, it's well thought out, there's outlines written, everyone's agreed upon it. This outline, there were some things added, and the final purge that was agreed upon that, well, not everyone agreed upon, we just did it. My leak meter told me something was wrong, and it was just a flash. It told me and I didn't listen. You know, you're in scape, let's move along. There's a lot of collateral damage.
It had pretty much covered half the floor in green liquid.
While the tile got eaten up, the next day they were just falling off. They had to pull a lot of blankets got scrapped. You know, there's some structures work, corrosion up in there.
Determined to send the FRCS back to the orbiter processing facility on schedule, cleanup operations continued around the clock. Numerous blankets, including the blankets underneath the drain lines, were damaged and had to be replaced. But in the rush to repair the damage, the new blankets were installed over the drain lines instead of behind.
The design intent obviously was to install the blanket underneath the line because we have access slits on the blanket to provide that access. We typically install blankets against the structure in almost all cases. So just a typical installation would go against the structure. We have access slits which allow us to do so.
But the original engineering drawing from 1984 was never changed to show why the slit was in the blanket and did not clearly indicate that the blanket was supposed to reside under the drain line.
All I can say is the drawing should have been more clear.
Both blankets were installed incorrectly, and since the work on the FRCS was being performed in the hypergolic maintenance facility and Discovery was in the orbiter processing facility, the technicians had no way of knowing the blankets would be in front of the vent ports when the FRCS was remated with Discovery. As the team wrapped up their investigation, the last unanswered questions were why did the closeout photos show the blanket properly installed? And even more importantly, how could the blankets be repaired without causing more problems so Discovery could fly again? An engineering drawing that was not updated, a crew cabin leak that required the removal of the forward reaction control system, a deadly oxidizer spill, and then a wrong blanket installation. Events that all culminated in the dangerous pressures recorded in the early moments of Discovery's launch on July 4, 2006. The final mystery was why did the photos taken after the blankets were installed show the blankets properly installed under the drain lines? A technician had mislabeled the photos, and the investigation team had reviewed closeout photos for Space Shuttle Endeavour instead of Discovery. The actual photos from Discovery were located and clearly show the blankets over the drain lines. A costly mistake that misled the investigation team into thinking the blankets were installed correctly.
I think that's the greatest lesson learned is we need to understand not just your piece, but how the whole system fits together, because everybody has their own perspective, and when you get to see the big picture, it actually changes your perspective of how important your role is.
The blankets had to be repaired before Discovery could fly again, and removing the FRCS again would introduce new risks. Some innovative technicians solved the problem.
We were suspended upside down for up to 20 minutes at a time.
The access was very hard to get into. We both held each other by our feet and our belts. Pretty much what I did is I worked one-handed, take the blanket and fit it right underneath the line. We went through the electrical access doors and the FRCS.
Combination of holding each other and while upside down, holding yourself on one of the support beams inside the FRCS.
They were able to get down in there, very difficult, and work the blankets in behind the drain lines and do it a couple ties single-handedly and fix the problem for us.
NASA learns from their mistakes. Changes were made to ensure these space mistakes never happened again for as long as the space shuttle was expected to fly.
Well, now the installation drawing clearly shows a section, a view, showing the blanket installed underneath the line, clearly, and there's also a general note that says, make sure the blanket is installed underneath the line. It says why, to limit billowing so the blanket does not intrude into the vent.
We're hooking in sight glasses, we're doing different purges, we're purging longer, verify that there is no liquid in there, we'll be able to see that it's gone. Should be fine.
The Space Shuttle program symbolized the greatest of human engineering, a complex space transportation system that enabled the construction of the International Space Station and enabled discoveries that altered our understanding of life on Earth and our place in the universe. As humans continue to reach for the stars and are driven by the spirit of exploration, sometimes things go wrong. Minor mistakes can cascade into major problems, but the astronauts, technicians, and engineers who have dedicated themselves to exploring space will never let mistakes stop them. They innovate, fix the problems, and ultimately become better. To go further and discover more. NASA wants to place humans on Mars. Plans for the roughly 35 million mile mission are in work. Because the Martian orbit around the Sun takes almost 2 years, a human mission to Mars is a 2-year commitment. But you can't just hop a rocket to Mars. Years of research and analysis have been completed, and efforts continue as NASA works toward the goal of placing humans on Mars by the year 2035. For the past 40 years, probes and then rovers have been investigating Mars, providing critical data. But it hasn't been easy. Mishaps and failures have threatened to derail NASA's efforts. In 1999, the $125 million Mars Climate Orbiter disintegrated because engineers did not convert English units of measure to metric units. A simple mistake that caused the spacecraft to think it was much farther from the planet's surface than it actually was. The result? It burned up in the atmosphere. Then, less than 3 months later, the Mars Polar Lander crashed on the surface of Mars because software incorrectly interpreted deployment of the landing gear as surface touchdown, resulting in the crash and complete loss of the mission, and the loss of another $120 million. NASA learned from their mistakes, refocused their efforts, and launched the Mars Exploration Rovers program. The program objective was to send 2 almost identical rovers named Spirit and Opportunity to investigate the surface of Mars. The 2 spacecraft would launch less than a month apart in 2003 in the critical orbital window when Mars was closest. If they did not make that window, NASA would have to wait another 2 years before launching the missions. And this time, with an $820 million budget, everything had to go right. So NASA constructed a surface system test bed called a Dynamic Test Model, or DTM. In NASA lingo, a MIR SSTB DTM. This MIR replica was created as an almost identical twin to Spirit and Opportunity. It carries many of the same electronics, hardware, research tools, and communications capabilities as a real rover. Many of the design specifications and functionality of the real MIR would be tested using the DTM. But as the launch date approached and engineers were testing a series of mission-critical procedures, a dangerous mishap occurred that once again threatened to derail the fragile trust NASA was rebuilding for its efforts to explore the red planet.
I was the test conductor that day. Next on the list was the high-gain antenna pinpuller. It was just another event.
In this particular case, we were operating basically in a nominal sense, and then we had standoff. The personnel standoff was what we felt at the time was an acceptable distance. We were following protocol.
We were just doing our standard sequence of, okay, is everybody ready? Do the countdown.
Okay, ready for countdown? 5, 4, 3, 2, 1.
Engineers and technicians are stunned as fire and smoke confirm the failed test. Tense moments follow as everyone in the room realizes an unidentified object flew past them at a dangerous velocity. Fortunately, everyone is okay, and technicians quickly power down the DTM and secure the area.
Instead of the usual little pop, it was a big bang.
We weren't really sure what happened. There was just a loud explosion and parts flying around. The safety of the technicians actually was jeopardized. It was a close call, a very serious close call.
A close call that NASA would discover put the life and health of the technicians at risk. And beyond the safety concerns, the narrow launch window was bearing down on the engineering team. NASA needed answers, and fast. With launch day approaching, and many more tests scheduled before the Mars exploration rovers could be cleared for launch, test engineers searched for answers.
If we are days or a week late in arriving at the launch pad, we may not be able to launch to Mars for another 2 years.
When the dangerous mishap occurred, technicians were conducting what is called a pyroshock test. Tiny explosive charges are used to deploy mechanisms during EDL, or entry, descent, and landing. A pyroshock test measures the amount of vibration or shock caused by the pyrotechnic explosion. Since MIR is loaded with sensitive research equipment, it is important to ensure the vibrations do not damage sensitive electronics or other hardware.
All of our spacecraft have multiple pyromechanisms on them. They're involved in releases, separations, and deployments. One of the drawbacks to using pyrotechnics is the basic pyroshock, or the fact that they go bang. Some are fairly modest, some are actually quite energetic. The mechanism may be located adjacent to a sensitive piece of electronic equipment. What's the effect of this pyromechanism on this piece of avionic equipment that's next to it or underneath it?
For the most part, pyro tests, even though maybe they sound bad, they typically are very boring.
But today's test was anything but boring. After the rover was secured, technicians began to discover the aftermath of the test failure. First, a deep gouge was observed in the camera mast surface. Something obviously had been shot out at a very high velocity and with substantial power. Damage to the wall behind the technicians confirmed that whatever shot out of the DTM had traveled dangerously close to the testing table and the technicians. Lying nearby, a small metal shaft was discovered. The shaft was identified as being part of a pyro mechanism called a pin puller. In fact, it was the piston from inside the pin puller used to release the high-gain communication antenna.
Basically, everybody in that room, if we would have been in the way of the pin puller, it wouldn't have been a good day for that person. That probably would have hurt, a lot.
As the MER approaches Mars, NASA sends a final command for entry, descent, and landing. This command starts a series of events, including orbital insertion, parachute deployment, landing, and the process of unpacking the rover. Once this sequence is started, NASA cannot send commands to the spacecraft until all the automated steps are complete. After landing, one of the most critical operations is to deploy the high-gain communications antenna. It is a round, plate-shaped antenna and is the primary communications antenna. Researchers will depend on it for receiving commands, including telling the rover where to go, as well as uploading data and large high-res images of the Martian surface. It has the unique capability to turn and beam a signal directly to a receiving antenna on Earth, or relay its signal through orbiting spacecraft like Mars Odyssey and Mars Global Surveyor. A second low-power omnidirectional antenna is also aboard the MER and sends signals in every direction, which is received by the deep space network of antennas on Earth, but its capabilities are vastly inferior to the high-gain antenna with slow data transfers and limited reception. If the high-gain antenna fails to deploy properly, MER will not be able to fulfill its mission objectives. And if the low-gain antenna were to fail as well, there would be no way to communicate effectively with the MER. This would result in a fully functioning rover that would never move again. Mission failure. The pin puller pyro shock test was extremely critical.
Turns out pin pullers are some of the highest shock sources. It's the most violent action. And so it causes a lot of shock, and for nearby hardware, whether it's a motor or something else, we have to make sure that the hardware survives.
Pyro pin puller consists of a housing, of a little pyro cartridge that actually provides the explosive force to drive the mechanism. There's a piston. The piston is engaged in the housing and protrudes from the front and is used to lock something in place. You fire the pyro cartridge, the gas pressure drives the piston back, releases the mechanism. After it releases, the piston slams against the cap, which is what produces the shock that we're concerned about.
The critical high-gain antenna is locked and held down by the pin puller. The piston secures the antenna in place. The pin puller housing contains two chambers filled with explosive charges. The charges are electronically activated. This creates a tremendous pressure buildup that moves the piston back against the cap, which creates the pyro shock. The antenna is released and then deploys, and if all goes according to plan, will begin sending information and receiving instructions from mission control and beam the first high-resolution images from the surface of Mars. This pin puller test resulted in the piston lying on the floor. An inspection of the pin puller housing revealed that the cap had been blown off, allowing the piston to shoot out. Dozens of pyro tests had been conducted during MER processing, and NASA had no record of a similar incident. Engineers and technicians were starting to understand what happened, but needed to know how, and perhaps more importantly, why. If the high-gain antenna pin puller did not work on Mars, the $820 million mission could fail. When the pin puller failed, MER engineers were in the middle of an aggressive 6-day testing sequence. With many more tests to conduct and an unforgiving schedule, testing had to continue. The DTM was extensively inspected, and no other damage was found besides the gouge in the camera mast. Electronics were checked, and all systems were go.
They wanted to continue testing, so we implemented what we felt to be a very safe and secure methodology in that we put barriers up.
Plexiglass, basically shield in between the 1 or 2 people that had to stay in the room to conduct the test and the equipment under test.
As testing continued, engineers began to search for answers. Had the pin puller been installed incorrectly? Was there a design flaw or a flawed part? Were there other pin pullers already installed for this test schedule that would fail? Were the test parameters normal? Sometimes, hardware is tested beyond norms on the DTM to analyze hardware limits.
Sometimes we do more to the DTM. We kind of over-test it to help us have confidence in the flight hardware and keep us from maybe over-testing and risking breaking things on the flight hardware.
The investigation team confirmed the parameters for the test were normal, and no other previous tests in the area would have contributed to the failure. Next, the test processes and safety procedures were thoroughly reviewed.
And our procedures were reviewed multiple times by safety and other folks to assure that everything else was in place relative to safety hazards.
Data from the failed test was analyzed to determine if the voltage used to activate the pin puller was correct. The data indicated it was correct. Curiously, it also showed that the amount of shock when the piston made contact with the cap was also within normal levels. This meant that the pyrotechnic event, the small explosion, would not have produced enough force to damage the cap. This also proved that the pin puller would have been configured and loaded correctly prior to the test. So how did the piston break through the cap? As the mystery grew, the obvious suspect was the pin puller itself, but so far, nothing could explain the failure. Each pin puller is good for 4 tests. After each test, it is refurbished.
Which consists of taking it apart, cleaning it up, repositioning the piston in its engaged position, and then firing it again.
It was confirmed that the failed pin puller had only been used in 1 previous test, and therefore was not beyond the 4-test limit. Because it had functioned correctly before, a fundamental flaw in the basic design seemed impossible. The investigation team reviewed the purchase of pin pullers. An initial order was placed several months before testing began.
Did our series of tests and began to run out of hardware. So we went back to the vendor that we procured these things from, and they had 4. So we procured those 4 units and used those in a series of tests. We refurbished them for an additional 4 firings.
The failed pin puller was traced back to one of the 4 extra pin pullers that were purchased after the original group. The design specifications and the purchasing paperwork were reviewed. The design specs were the same. But a comparative analysis was about to reveal the source of the fiery test failure, initiating an aggressive response to ensure safety while NASA scrambles to meet the critical launch window before it's too late. With a narrow launch window approaching, the Mars exploration rovers Spirit and Opportunity are being tested using a fully operational replica called a dynamic test model. Any delay could result in the mission being pushed back for 2 years due to the proximity of Mars to Earth during orbital cycles. A critical communication antenna pyro test fails, leaving NASA scrambling for answers. The pin puller, which holds and releases the antenna, is traced back to 4 extra pin pullers that were purchased after the original group. After extensive analysis and side-by-side comparisons, NASA finally discovers the cause of the failure. All of the pin pullers, including 3 of the 4 newly purchased units, have steel caps, but the one pin puller that failed had an aluminum cap. Finally, a breakthrough.
With a steel cap, it appears that they're capable of 3 to 4 firings. With an aluminum cap, they're only safe to be fired once.
The pin puller had been used in 1 previous test successfully. It was refurbished and installed for the high-gain antenna test. But this time, when the pin puller charge was activated, forcing the piston back, the aluminum cap was too weak, and in an explosion of fire and smoke, the piston forced the cap off, shot out of the housing with extreme force, ricocheted off the camera mast, then flew dangerously across the room toward the test technicians. The aluminum cap was too weak to withstand multiple firings. This was confirmed when the cap was recovered from the test area. Space is a dangerous business, and although the direct cause of the failure was now known, the reason the cap was different had to be determined. When the pin puller fires on Mars, an unforgiving and alien environment, it must work. The investigation team begins meeting with suppliers and reviewing all purchasing activities.
When we went back and looked carefully at the design, it turned out that they had sold us units from 2 different lots.
The supplier of the pin pullers only had 3 extra pin pullers made with steel caps. In an effort to meet NASA's need quickly, they supplied a pin puller from a production run a couple of years earlier. Those were designed with the aluminum caps.
Not exactly a design flaw, but a design deficiency in that it had an aluminum cap. It put it into an aluminum housing, as opposed to our design and the more recent other designs that had a steel cap that were much more robust.
When engineers created the specifications for the MER program, they did not communicate to the supplier that the pin pullers would be refurbished and used multiple times. From the supplier's perspective, the older unit with the aluminum cap met the required specifications. They saw no reason to communicate the difference in cap material.
It just happened that since we went back to 2 successive earlier designs that we were not fully aware of it, and it wouldn't have been something that the vendor would have necessarily either acknowledged or known about or revealed to us. It wouldn't have, they don't assume that you're firing these things more than once.
But why wasn't the difference caught after the part arrived at NASA? Is it impossible to tell the difference between the aluminum and steel caps? And after the pin puller with the aluminum cap was used once, did it look any different than usual?
The signs of catastrophic wear are obvious if you're careful enough to look for it.
When the failed pin puller was examined, it was clear that the structural integrity of the hardware had been damaged prior to the failure. The threads of the cap were stripped. Why was this not noticed during the refurbishment process? The investigation team began looking into the process and criteria for refurbishment. They discovered that there was no defined process. Refurbishment was performed without any formal procedures, and the process was only known by the technicians who had been refurbishing the pyros for years.
It wasn't a particularly formal process up until this point. It was just something done by people who were familiar enough with it to do it.
The aluminum cap could have been identified at several checkpoints throughout the process, especially when it was damaged after the first test. But a lack of formalized procedures contributed to the dangerous test failure and a false sense of security.
The history was, nothing really ever goes wrong, quote unquote, with pyro tests.
When you're dealing with these kinds of mechanisms that sometimes appear quite benign, because some of them go, as I mentioned before, they go bang, and some of them just go click. So you can forget about the fact that you're actually dealing with explosives.
That might have maybe made some of us complacent or not so worried.
You need to be more careful.
NASA learns from its mistakes, but would changes to processes and safety procedures pay off? Launch day was almost here. A routine pyro shock test became a hazardous situation in less than 1 millisecond. A series of problems combined to form the perfect storm for the accident. NASA specs that did not clearly require steel caps. A supplier's failure to communicate the change in material. NASA's failure to communicate the pin pullers were refurbished and reused. A general complacency about pyro tests. And a refurbishment process that had no formal guidelines and therefore failed to look for signs of structural failure or material changes. Safety and procedural changes were implemented to ensure this kind of space mistake never happens again.
Any pyrotechnic testing is done remotely now. That's to protect the people, obviously, but also to protect critical hardware.
Where we actually have flight hardware or critical ground test hardware around, we have to get the refurbishment process witnessed by QA representatives. For less formal testing, we just have a check-off procedure where we verify that the integrity of the parts.
But would all the technical and safety changes, along with the improved open communication between all departments and suppliers, produce results? On June 10, 2003, Spirit lifted off and headed to Mars. Opportunity followed closely behind on July 7, 2003. The launch schedule had been met with little room to spare. For the next 7 months, NASA and the world wait as the spacecraft makes the 35-million-mile journey to the Red Planet.
Current altitude 8,000
On January
feet.
10, 2004, Mission Control at NASA's Jet Propulsion Laboratory sends the command for Spirit to begin
All
EDL.
systems are go for entry descent landing. We are roughly 11 minutes 48 seconds from landing at the Gusev crater in the southern hemisphere of Mars. Atmospheric entry in 3, 2, 1.
The spacecraft enters the atmosphere at 12,000 miles per hour, and within just 6 minutes will have to slow to 0 upon touchdown, except for low-frequency radio tones confirming certain EDL events.
Parachute detected.
Mission Control has no communication with Spirit until landing is complete. The first confirmation of landing will be sent about 14 minutes after touchdown. Then, after about 6 more minutes, if everything goes right, the signal will reach Earth and confirm Spirit rests safely on the surface of Mars. This was the moment, just under 5 years earlier, that Mission Control witnessed the destruction of both the Mars Climate Orbiter and the Mars Polar Lander. The atmosphere in Mission Control could not be more tense. Years, hundreds of millions of dollars, and people's careers are all invested in this moment.
Retro-rocket ignition has occurred. At this point in time, we should be on the ground. However, we currently do not have signal from the spacecraft. Deep Space Network tracking stations at Canberra and Goldstone are still searching for the primary signal.
What do we see?
All systems confirm the landing has been a success. Then, 2.5 hours later, the world would see the first MER rover images from the surface of Mars. 21 days later, in a different remote location on Mars, Opportunity also lands successfully. The Mars Exploration Rover program will go down as one of the most successful planetary exploration programs in history. Combined, Spirit and Opportunity have sent back over 250,000 images of Mars, and Opportunity has traveled over 13 kilometers, breaking the distance record of any other space vehicle. NASA even named 2 asteroids after Spirit and Opportunity as their way of honoring the 2 now legendary robotic explorers. The mission was originally planned for just 90 days, but was given 5 mission extensions. Spirit remained operational and sending historic science data for 6 years, 2 months, and 19 days before losing contact March 22, 2010. Opportunity, however, has remained functional for an astonishing 13 years plus of scientific discovery on Mars. Only time will tell how much longer Opportunity will remain functional. Today, it is working with NASA's newest rover, Curiosity, searching for evidence of ancient life on Mars. MER laid the foundation for successful programs like Curiosity and ultimately for placing humans on Mars. When exploring the unknown and pushing science beyond anything attempted before, space mistakes will happen, but the astronauts, technicians, and engineers who have dedicated themselves to exploring space will never let mistakes stop them. They innovate, fix the problems, and ultimately become better to go further and discover more. January 16, 2003, Space Shuttle Columbia lifted off from Launch Complex 39A at Kennedy Space Center. 16 days later, after completing the mission objectives, Columbia broke apart during re-entry, resulting in total loss of vehicle and crew. For 2.5 years, NASA's launch pads sat empty, a solemn reminder that space is a risky business. The shuttle fleet was grounded, and the world wondered if NASA would ever launch another space shuttle. Behind the scenes, NASA worked tirelessly to return to flight. NASA undertook a massive recertification and verification process that evaluated all of the space shuttle's critical systems, while at the same time addressing external tank foam debris which was determined to be the primary cause of the accident. NASA set May 2005 as the target launch window for return to flight. But when a critical external tank test fails, NASA scraps the launch date and is forced into a new investigation that reveals a tangled web of space mistakes that threaten to once again derail the entire Space Shuttle program. But first, during the orbiter recertification process, a chilling space mistake was uncovered when a rudder speed brake actuator was opened for the first time in 20 years. When the orbiter returns from space, it becomes a high-tech glider during descent and landing. With no power, slight course corrections and deceleration maneuvers are performed using the wing and body flaps and the rudder speed brake. The rudder speed brake is controlled by actuators in the tail section. As the orbiter approaches the landing strip, the rudder speed brake is used for aerodynamic braking to aid in slowing the orbiter. At a descent angle 7 times steeper than a commercial aircraft and traveling 220 miles per hour, the rear wheels touch down. A drag chute is deployed, followed by the nose gear touchdown. The rudder speed brake is then fully deployed. 30 seconds later, the orbiter has slowed to less than 68 miles per hour. The drag chute is released, and the orbiter coasts to a stop. During recertification, all 3 orbiters, Discovery, Atlantis, and Endeavour, reside in orbiter processing facilities 1, 2, and 3 at Kennedy Space Center. Surrounded by access platforms and support structures, the orbiters are barely recognizable. New carbon fiber material is being placed on the wing leading edges and nose cone sections. Thermal protection system tiles are replaced by hand, and landing gear systems are tested. The return-to-flight launch window is now less than a year away. NASA works multiple shifts in their attempt to complete all the required work on time. At the highest platform level, the tail of Discovery rises majestically above the mayhem. The actuators that control the rudder speed brake are to be checked next for recertification. The tail section contains 4 rudder speed brake actuators controlled by a power drive unit. Each actuator contains an inboard set of 9 planet gears and an outboard set of 9 planet gears. 2 shafts connecting the actuators to the power drive unit control the actuators, which work together to open and close the 2 speed brake flaps. But when the actuators are opened up, engineers are astonished to discover corrosion in the actuators and gears. But even more shocking, they discover that one of the actuator's planet gear sets are reversed.
As we were exploring where the corrosion was and what caused the corrosion, we noticed that the wear marks on the gears didn't line up just the way we thought they should. And it was at that point we discovered that we had reversed the planet gears.
There are 2 sets of planet gears, and they had been installed in the reverse direction from how they should have been. Basically, they've been swapped out.
An analysis of the gears revealed that the outboard gears were slightly smaller than the inboard gears. When configured correctly, 9 of the smaller gears are in the top or outboard half of the actuator, and 9 of the larger gears are in the bottom or inboard half of the actuator. However, engineers discovered that in one of Discovery's actuators, the 9 smaller gears were in the bottom and all 9 of the larger gears were in the top. If the rudder speed brake fails, Discovery, Atlantis, or Endeavour could be destroyed on landing. Return to flight just got a lot more complicated. With return to flight activities rushing forward, a new investigation is launched to determine how the rudder speed brake actuator, or RSBA gears, could have been reversed. The mistake also raises concern for the gears on Atlantis and Endeavour. The incorrectly installed gears reduce the overall strength margin of the actuator.
You don't get full tooth engagement. You've only got part of your teeth engaging, therefore it results in a higher stress state for the gears that are engaged.
And could result in a critical failure if the gears fail during flight. The orbiter would land traveling much faster than normal. When the drag chute deployed, the air resistance would have been too great, forcing the nose landing gear to slam into the ground. The massive high-speed stress would break the landing gear, resulting in the nose hitting the runway and the orbiter losing complete control with catastrophic results. Even if the issue was noticed in time and the drag chute was not deployed, the increased landing speed could have caused the orbiter to exhaust the entire runway, crashing in the swamp on the north end. The rudder speed brake is a single point of failure and could not be more critical to the landing sequence. But Discovery had flown 30 missions and landed successfully each time. Further investigation revealed that the gears in the other 3 actuators on Discovery were installed correctly. This time, NASA caught a break.
We were lucky in this case that it was the lowest loaded actuator that was put together incorrectly, and as a result, we didn't have any problems.
Because the only actuator that was affected on Discovery was the highest actuator out of the 4, it bore the least amount of stress during speed brake operation. The wear and tear on the gears was evident, however, and could have been just a matter of time before the gears failed. Atlantis and Endeavour were both inspected. NASA is relieved that no other Planet gear sets are installed incorrectly. However, when NASA begins to replace the worn-out and misassembled actuator with a spare actuator, they discover the same problem in the spare unit. Engineers immediately began to develop solutions to make sure this space mistake never happens again. An extensive investigation revealed that during the original assembly of the gears into the actuators, technicians became confused for 2 reasons. First, the gears in each of the 4 actuators are all installed differently because each actuator supports different loads. An analysis revealed that if the gears in the incorrect upper actuator, actuator number 4, had been installed in the actuator 1 position lower in the actuator 3 housing, then surprisingly, the gears would have been in the correct position for that actuator. It was surmised that the technicians may have assembled the 3rd actuator and then assembled the 4th using the same gear order. Secondly, the top and bottom gear sets look almost identical in size. To eliminate the confusion, engineers developed special tools for each set of Planet gears.
As part of our mistake-proofing process, we actually went back and designed dedicated fixtures to each actuator that also have physical limitations, such that if you use the right tooling for the right actuator, you'll be unable to assemble it swapped out gear sets.
This example of mistake-proof engineering eliminates any guesswork because one tool can only be used with the bottom gears, and a different tool can only be used with the top gears. This ensures that the gears cannot be installed incorrectly again, as long as the technician uses the newly designed tool. The spare actuator unit was repaired successfully and installed on Discovery. The remaining mystery was why had this problem never been noticed before?
The initial requirement for the rudder speed brake system was 100 missions. However, the time for that was 10 years. Now, as it turns out, we went 20 years without looking at them.
The mistake was not found sooner because the actuators were certified for the original flight life of the space shuttle, 10 years, 100 missions. Due to budget constraints and realigned program objectives, the space shuttle flight schedule was never as aggressive as anticipated when the program began flying in 1981. So although the affected actuator had been installed for double the 10 years, it had only flown 30 times, so it was still considered under the original certification. NASA learns from their mistakes and is applying these lessons to the new exploration programs.
When you manufacture something as critical as the flight control surface actuators for those things like the space shuttle, they have to work. And they have to work consistently, and they have to work every time.
Create mistake-proof designs such that put components in that can only be installed one way, take out the human element that could potentially make an error putting that together.
Look at how you're going to assemble things. We tend to engineering tends to dominate the design, and without necessarily considering all the implications of assembly.
With the RSBA issue resolved and the massive recertification effort now complete, a launch date is set. Discovery is made into a new external tank and solid rocket boosters and prepped for launch. Finally, the space shuttle's long-awaited return to flight seems imminent until a shocking discovery reveals a space mistake with disastrous consequences. NASA sets May 2005 as the target launch window for return to flight. Kennedy Space Center buzzes with excitement as the long-awaited return-to-flight launch window finally approaches. It has been an arduous 2 years and 3 months since a space shuttle has flown. But just as NASA is poised to overcome the tragic loss of Columbia and get back to the business of building the International Space Station, 700 miles away on the edge of the Louisiana Bayou, a phone call is about to change everything. NASA's Michoud Assembly Facility, or MAF, held the world's record as the largest enclosed building on Earth for over 20 years. It is hallowed ground in the space industry. MAF was the original manufacturing facility of the massive Saturn V rocket, the rocket that carried the first humans to the moon. The space shuttle is comprised of the orbiter, the space shuttle main engines, the solid rocket boosters, and the external tank, or ET. The 154-foot external tank supplies fuel to the space shuttle main engines during launch and ascent. The aluminum lithium alloy tank is comprised of 2 fuel tanks. The forward tank, called the LOX tank, contains 146,000 gallons of liquid oxygen. The rear LH2 tank contains 395,000 gallons of liquid hydrogen. MAF was the obvious choice to manufacture the space shuttle's external tanks. Some of the largest tools in the world were constructed inside the facility to build the massive liquid oxygen and liquid hydrogen tanks. Unlike the solid rocket boosters, which are retrieved, refurbished, and reused after every launch, the ET is disposable, splashing down and disintegrating in the Indian Ocean. So every space shuttle launch requires a new ET. MAF is a busy place. Prior to Columbia, 113 completed external tanks rolled out of MAF were loaded on specialized barges, then transported by water along the coast of the Gulf of Mexico, around Florida, and delivered to Kennedy Space Center. After the Columbia accident was blamed on foam loss from the external tank, morale at MAF has been low. With return to flight approaching, a renewed optimism is returning. But less than 45 days before the launch date, a company interested in supplying a metal screen material used in the external tank contacts engineers at MAF with a disturbing discovery.
When they compared that screen they were going to buy with the screen that was on existing parts, they noticed there's a difference.
The company was interested in creating and supplying the screen material used on a critical piece of hardware called a diffuser. The diffusers are used in the top of both the liquid oxygen tank and liquid hydrogen tanks.
When we launch, the liquid level of the tanks start to drop. And so we put ullage pressure back into the top of the tank. When the liquid level is dropping in the tank, you're forming a vacuum. So you don't want the tank to collapse on itself, so you're putting pressure back in through the top. And the diffuser disperses it into the tank so it doesn't all go in one spot, cause something to be too hot, one area too cold.
As the liquid hydrogen and liquid oxygen are consumed during launch and ascent, gaseous hydrogen and oxygen are pumped back into the respective tanks. The gas is dispersed by the diffuser at a finely calibrated dispersion rate, matching the drain rate of the liquid fuel. If the rate is off or restricted, the massive vacuum pressure inside the tank would begin to resist the fuel flow and could cause the tank to collapse, creating a catastrophic failure. The company interested in supplying material for the diffusers had requested several samples of the screen material to determine if they could meet the specifications. But when they analyzed the samples, they discovered that there were 2 different types of screen material. With Space Shuttle Discovery fully stacked and almost ready for flight, NASA launches an emergency investigation. Which screen material was correct? Were any diffusers made with the wrong material? And if so, would it affect their performance? And most importantly, which material was used on the diffusers in the external tank currently scheduled for launch? The specter of a delayed launch began to overshadow NASA's imminent return to flight. And for this space mistake, the worst possible scenario was about to come true. A company interested in supplying the screen material for the gaseous hydrogen and gaseous oxygen diffusers used in the Space Shuttle external tanks discovers that 2 different types of material were provided as examples of the required screen material. The diffuser is comprised of a hollow metal core with a wire mesh screen around it. The design of the mesh is known as a plain Dutch weave. When the company analyzed the 2 screen materials, they discovered that some of the material was the required plain Dutch weave, but the other samples were a duplex plain Dutch weave.
Using unaided eye, you will not be able to see a difference in these 2 screens. But if you held a piece of the sample or a sample of the material in your hands, you would notice that one was slightly stiffer. And then if you used magnification, which we found at least 10x, you could see that there was a different amount of wires per inch.
So when you have a weave of screen material, you have one wire that I guess you would call static or a warp wire, and then the other wire bends around that. So a plain Dutch weave has one wire, and then the other wires get bent around it. A duplex has actually two wires, and then the wire gets bent around it.
Through analysis and testing, the investigation team confirmed that the duplex plain Dutch weave was not acceptable because it would restrict the uniform flow of ullage pressure and gases, restricting or stopping the flow of gases back into the tank while the liquid fuel rushes out to fuel the space shuttle's main engines could cause stress on the tanks and even the catastrophic collapse of the tank. Even with a minimal reduction in ullage gases, the vacuum inside the tanks could restrict fuel transfer to the main engines, which would not allow the orbiter to complete launch and ascent, resulting in a catastrophic failure and loss of vehicle and crew. NASA's investigation team begins to work around the clock to determine if any one of the diffusers currently installed in external tanks were made with the wrong screen material. While they can test the assembled diffusers in inventory by direct analysis, the diffusers inside the completed external tanks could not be accessed. Shocked, the investigation team discovers that 15 of the 21 diffusers in inventory were constructed with the wrong material. The likelihood of faulty diffusers in completed external tanks was increasing. The investigation team traces the wrong material to a different company that had supplied screen material years earlier. That company delivered both the correct plain Dutch weave and for some reason also supplied the wrong duplex plain Dutch weave under the same part number. Then the company went out of business, which was why NASA was seeking a new supplier for the screen material in the first place. As the feverish investigation continues, Space Shuttle Discovery is moved to the launch pad. But are the diffusers inside the external tank faulty? NASA needed answers, and fast. While the investigation reaches a feverish pitch at the Michoud Assembly Facility in New Orleans, Discovery begins launch preparations at Kennedy Space Center in Florida. The shuttle is moved to Launch Pad 39B, and on April 14, 2005, a critical tanking test is performed. The test is standard procedure in advance of a launch, but today's test is anything but standard. The external tank is filled with liquid hydrogen and liquid oxygen, and as Mission Control begins testing, a liquid hydrogen pressurization relief valve begins to act strangely. The valve is designed to open and close to ensure the liquid hydrogen stays at the correct temperature, but this time it is cycling more often than normal. Then suddenly, engineers begin receiving intermittent readings from the liquid hydrogen sensors. The sensors serve as fuel gauges and are responsible for sending the signal to the main engines when the fuel is depleted and the engine should shut off, called MECO, or main engine cutoff. The test is a failure. Afterwards, a full system check and analysis indicate the probability of a problem with the hydrogen tank diffuser. The mid-May launch is scrapped, and in an unprecedented move, the fully stacked space shuttle is returned to the vehicle assembly building. NASA's celebrated return to flight remains elusive. Meanwhile, back at MAF, the investigation team concludes a thorough review of the documentation created during processing of all of the diffusers. They were able to identify which rolls of the screen material were wrong, and then track it through the assembly and installation process to discover if any diffusers in completed external tanks contained the faulty screen material. The results were disheartening.
In inventory and installed on tanks, we had 31 diffusers that were made out of the wrong material.
It was 21 GH2 and 10 GO2.
Out of 26 diffusers installed in 13 completed external tanks, 16 diffusers are faulty. And unfortunately, the team confirms that the hydrogen diffuser in Discovery's return-to-flight tank is also one of the faulty diffusers. Back at Kennedy Space Center, the space shuttle is destacked for only the 8th time in the program's history. All the return-to-flight momentum seems to have dissipated. A recovery plan is quickly put in place. Because of the failed tanking test and other issues, NASA does not want to use Discovery's tank. An external tank for Space Shuttle Atlantis is already at Kennedy Space Center and stored in the Vehicle Assembly Building. Its diffusers are faulty as well, but MAF sends a team of 30 engineers and technicians to replace the bad diffusers. This will be quicker and less risky than shipping another tank by barge from MAF. Also, the extra tank is already prepped to all the return-to-flight certification requirements and is essentially ready to go.
30 people went down to the Cape for us to go down and remove and replace those diffusers, which was something we've never done before. Remove and replace a diffuser at the Cape, it's never happened before. Whole new learning curve. Actually, I think it was a learning curve just trying to remove and replace one here, because we've never done it before.
Because the company that supplied the incorrect duplex plain Dutch weave went out of business, the investigation team could not discover why the wrong material was delivered. NASA learns from their mistakes. All future screen material was inspected by magnification to confirm the thread count and wire configuration, even if the paperwork says it's correct. The specification paperwork was also updated to clarify the demand for a single static or warp wire and not a double wire. July 26, 2005. Once again, the world watches as NASA makes another attempt to return to flight. Tension is high. In a little over 3 months since the failed tanking test, Discovery is once more poised for launch. As the crew heads to the launch pad, NASA's engineers and technicians, along with all the companies that contribute to the space shuttle, watch in hopeful anticipation. It has now been 2 years and 6 months since the last space shuttle slipped the surly bonds of Earth. But today, the space shuttle would fly once again. The successful return-to-flight mission led to the full reinstatement of the orbiter fleet and resumption of a full flight schedule. NASA was founded on the principles of exploration and pushing the limits of human achievement. As astronauts place their lives in the hands of engineers, technicians, and managers, mistakes will happen, but the lure of the unknown and the thrill of discovery continue to inspire humans to develop safer, more powerful spacecraft and to reach beyond our planet to the stars, to go further and discover more. NASA's often forgotten predecessor, NACA, the National Advisory Committee on Aeronautics, was created in 1915 to compete with German aircraft design in World War I. NACA moved American aeronautics from those early wooden wire, cloth and a prayer biplanes of yesteryear to the world's very first supersonic flight of the rocket engine-powered X-1, piloted by future astronaut Charles Chuck Yeager in 1947. 11 years later, on October 1, 1958, to compete with Russia's successful launch of Sputnik, NASA was born. Between then and now, NASA has brought us the Mercury program, Gemini, and the first American spacewalk, Apollo and the Moon. 30 years of the Space Shuttle program and the International Space Station. Tomorrow, Mars and beyond. NASA's success with each groundbreaking achievement, from the distant past to the far future, depends on the knowledge gained and the technology developed for past programs. And while technology is fundamental to space travel, the most vital factor in NASA's successful journey into the great beyond is its people, their creativity, courage, and motivation, and their bold and endless drive to go where no one has gone before. Being human also means making mistakes. Decades of research has shown that most space failures are caused by human error.
Look for an impact.
An astonishing mistake sends a $100 million deep space probe spiraling out of control, dooming priceless cargo in a spectacular crash landing. But first, NASA is forced to scrap a critical and expensive piece of space shuttle hardware when a technician makes a wrong turn. NASA's highly sophisticated Coordinate Measuring Machine Probe, or CMM probe, measures machined parts on any axis, down to less than a micron. NASA's CMM probe is used, among other things, to measure components of the Space Shuttle orbiter's cold plates.
A cold plate is used to draw the heat from the LRU avionics and radios in the shuttle.
Inside the Space Shuttle orbiter, line replaceable units, or LRUs, including avionics boxes, control numerous critical functions of the orbiter. The LRUs produce a lot of heat, which cannot be traditionally vented or cooled because of the sealed environment inside the crew module. Cold plates are installed against the LRUs, and the heat is drawn off through convection, keeping the LRUs cool. Failure to cool the LRUs properly could be fatal to the crew. The cold plate's core material is machined into a single component that includes more than 30,000 individual protruding pins. The pins are designed to meticulously control the flow of coolant through the cold plates.
They have to be very precise because when we're done building the cold plates, they flow a fluid through them during testing, and it has to flow at a certain rate to make sure that it's going to flow fluid through enough to draw the heat out.
Machining those 30,000 pins is a precise, time-intensive, and expensive process, a process that can take weeks to complete a single cold plate.
You have about, I'd say, at least 80 manufacturing hours, probably 2 shifts, 2 weeks to machine that, because each one of the little pins in there is machined individually.
Then each and every one of those 30,000 pins must be checked to ensure that it meets precise dimensional requirements. This meticulous process is accomplished with the CMM probe.
They take detailed measures to make sure that everything matches the print requirements.
Operating the probe is fairly straightforward, but in a bizarre accident, many hours into the process of checking every pin, unexpectedly, everything goes wrong.
I was measuring the part. I need to move to the next area to measure. I need the machine to move upwards and over.
But instead of moving up, the probe suddenly goes down, damaging the cold plate and the CMM probe.
Instead of moving upwards, it went down. And during that time, it ended up damaging the part, causing a hole, a dent, and also the equipment at the same time.
Technicians are stunned and confused. A cold plate has never been damaged in the CMM probe shop. Why today? Was it a technology failure or operator error? NASA's investigation would reveal why a 15-year veteran operator's perfect record suddenly came to an end. A highly sophisticated coordinate measuring machine probe in the hands of a meticulous, experienced operator, and the unthinkable happens. A space shuttle cold plate is damaged, along with the mission-critical CMM probe. CMM probe operator Fred Vivier calls his supervisor immediately to tell him what happened, but he doesn't believe it at first.
It took Fred a while to convince me that that's what had actually happened. Some of my inspectors are practical jokers occasionally, so when he told me he'd done it, I just, nah, you didn't really do that. It took him about 20 minutes on the phone to convince me that they had actually done it, because you're talking a lot of man hours, a lot of machine hours into making that part.
Sick. A really bad sick feeling came over due to the type of part, time taken to make the part, and the criticalness of the part.
Fortunately, damage to the CMM probe is limited to the ruby tip on its stylus, which is quickly replaced. The cold plate's a different story.
The probe ended up springing into a very, very thin wall on the cold plate, causing a dent and a small hole.
The cold plate core is scrapped. It no longer meets NASA's strenuous safety requirements.
Pretty detrimental to the program at the time. We're trying to, meet a schedule.
So this set us back. We just had to go build another core.
Building another core would take at least 80 man-hours, a costly operation. Manufacturing a new cold plate and repairing the ruby-tipped stylus solves the hardware issue, but doesn't answer NASA's most pressing questions. How did it happen, and why? Questions that had to be answered before any other cold plates could be inspected. NASA could not risk damaging another mission-critical piece of hardware. NASA needed answers, and fast. The CMM probe involved in the accident was new. It replaced an older machine that had broken down. The machine's software and mechanical functions were working perfectly. But like so many other space mistakes through the years, the accident was a result of one simple human frailty: operator error. a 15-year skilled operator with a flawless record made a wrong turn, costing the space program tens of thousands of dollars and weeks in delays.
I mistakenly twisted it the wrong way and it went down instead of up.
But this was not a simple case of lack of attention to detail. The operator was one of the best in the business. Why did he make such a costly error?
There was no rush.
Knowing Fred as I do, he was concentrating on what he was doing.
I think it was the way the machine was set up.
Had that thing been oriented right, it would have never happened.
The old machine had different controls. The probe was controlled by 2 joysticks. The new CMM probe was controlled by a single, multifunctional joystick.
The one joystick will make it go up, down, right, left, forward, and backwards. If you twisted it clockwise, it would go up. If you twisted it counter, it would go up, it would go down.
But the cold plate was destroyed when the controller was turned the wrong way. While this might not be a big deal in your latest home improvement project, this was NASA, and this was unacceptable. The measurement of cold plates had to be foolproof. Investigators were closing in on both the root cause of the accident and a solution that would guarantee future success. When the new CMM probe was purchased, each technician spent hours training on the new machine.
Once we got it in here, all the folks went through some specialized training. That was part of the purchase contract with it. I had like 4 inspectors at that time. They all went through a week's worth of training with the company rep where we purchased the machine.
But the root cause came down to the human trait known as automaticity, a pattern or habit resulting from learning, repetition, and practice. Walking, driving a car, or always putting on your right shoe first are examples of automaticity. These ingrained habits are formed from years of repetition, even by some studies altering our brain patterns, making relearning or unlearning certain habits extremely difficult. The new controller required that the joystick be turned clockwise to go up, but the technicians were trained by years of experience that clockwise was always down.
I guess it's our American standards, righty-tighty, lefty-loosey. You know, you want it to go down, you turn it right. You want it to go up, you turn left.
1 week of intensive training on the new machine was not enough to counter years and years of subconscious habit. And putting more space shuttle hardware at risk while the technicians developed new habits was unacceptable. Through extensive coordination with the manufacturer of the new CMM probe and software engineers, the programming was altered to make the probe go up when turned counterclockwise and down when turned clockwise. This ensures the probe is far more intuitive for the operators. One additional fail-safe was put in place. Directional labels were added to the controller.
Have not had one problem since then. We label it, the folks look at it, they take the time they need. We haven't had any other issues at all.
Look for an impact.
Next, a spectacular crash incites a spectacular recovery effort to salvage a $100 million mission and billions of years of science. August 8, 2001. NASA launches a Delta II rocket out of Kennedy Space Center that carries an unmanned vehicle into a little heralded search for the origins of the universe. It's a quiet launch, except for the roar of the Delta II's engines. There are no lawn chairs on the beach, no space fans on top of campers, no massive crowds cheering as the Delta soars away from its launch pad. You'd think there would be, because this unique scientific mission is in many ways traveling back in time, billions of years to the very birth of our solar system. After years of preparation, the world's scientific community is filled with anticipation for what the spacecraft might bring back. The unmanned spaceship is called Genesis because it heads into space seeking answers about the beginning. Genesis is on its way to an orbit within an orbit, 1 million miles from Earth, in direct line with the Sun, to catch some rays and return them to Earth. The spacecraft is armed with a variety of unique collector arrays designed by NASA to capture the purest solar wind ions possible from the outer layer of the Sun. Scientific evidence suggests this outer layer hasn't changed since our solar system was born from its original nebula some 4.5 billion years ago. Ions in the solar wind have been called the fossils of that nebula, which means theoretically they should tell us if our solar system is made up of the same stuff that made up that original collection of ice, dust, and gas. If so, NASA believes those solar winds could also hold clues to the origins of life itself. The Genesis mission is the first time space matter has been returned to Earth in 3 decades since astronauts brought back samples from the moon. On November 16, 2001, Genesis slips into an elliptical orbit around Lagrange point L1. Lagrange points are gravity-balanced zones between celestial bodies, and L1 sits directly between the Sun and the Earth. As Genesis orbits L1, L1 orbits the Sun. L1 was selected as the focal point for this critical mission in part because at 1 million miles away, it is void of Earth's atmosphere and contamination. After establishing its orbit within an orbit, Genesis deploys its solar panels to draw energy from the Sun. Then, the primary collectors open and are exposed to the solar wind. The ions from the solar winds begin crashing into the collector arrays, traveling over 200 kilometers per hour, almost 25,000 miles per hour. On impact, the ions are buried into the surface of the collectors. The hexagon-shaped wafers consist of a variety of super-pure materials, including silicon, commercial sapphire, gold, and diamond-like carbon film, some expected to capture the elusive solar wind better than others. Secondary arrays are automatically deployed when Genesis encounters special solar wind, like coronal mass ejections. The purity of the ions is critical. NASA wants pristine fossils of the birth of the solar system if they are to have maximum scientific value. Throughout the years of planning and manufacturing, the collector arrays were handled with extreme care in clean room environments, with a focus on maintaining the critical purity required.
These samples will be available for the scientific community for decades to come.
For 850 Earth days, the solar wind blasts Genesis. Then, on April 1, 2004, after completing 5 halo loops of the Sun, the collector arrays are retracted and stored in the Sample Return Capsule, or SRC. Then Genesis begins its million-mile journey back to the future. Genesis has spent 2.5 years collecting the solar wind ions. The final phase of the mission will be the SRC's entry, descent, and landing. NASA is not taking any chances. An elaborate EDL is planned to ensure the capsule returns as gently and safely as possible to protect its ancient cargo. Traveling over 24,000 miles per hour, Genesis would smash into Earth's atmosphere and immediately begin slowing from the atmospheric resistance. This rapid deceleration triggers a series of mechanical events that deploy a drogue parachute, which stabilizes the SRC and slows the spacecraft's descent. The SRC continues to slow until it is 6.7 kilometers high. The drogue chute is released, and a large parafoil is deployed to further slow the descent and leave the return capsule in stable flight. Then, to further safeguard the precious cargo, a helicopter with a 5-meter-long hook would capture Genesis by its parachute and gently lower the spacecraft to the ground. NASA selects the United States Army's Dugway Proving Grounds as the landing site. Located about 85 miles southwest of Salt Lake City, Utah, it is a vast desert wasteland. Founded in 1942 and notorious for top-secret chemical and biological warfare testing, including the rumored release of the nerve agent VX in 1968, killing over 6,000 sheep 30 miles away from its test site, and the production and mishandling of live anthrax as recently as May 2015, Dugway is highly guarded and its airspace is restricted. It provides a vast, isolated area for the landing of the Genesis capsule. Weeks in advance of Genesis' return, NASA rehearses the mid-air capture multiple times.
We're 6 November. You got a tally on a parafoil?
Scientists around the world have been waiting for 3 long years for Genesis' return. NASA is ready, confident in their recovery plan. Genesis sample return capsule enters the atmosphere right on time on September 8, 2004. But then, everything goes wrong. The capsule begins spinning wildly out of control, plummeting to the Earth at hundreds of miles per hour, leaving NASA scrambling to save the mission. Stunned, NASA watches helplessly as the capsule filled with the mysteries of our solar system plunges to Earth.
Vertigo Mach, your range is 10 miles now, sir. It's coming down through 200,000 feet. 10 miles, 200,000 feet, thank you.
Manager, we are able to identify a tumbling object, and Mission Manager MTC, be advised, from our vantage point, we do not see a drogue chute. Negative drogue.
Copy.
NASA pulls back the recovery team, including the mid-air capture helicopters. Because the parachute deployment sequence is a fail-safe mechanical system triggered by re-entry, there is nothing NASA can do to activate the parachutes.
It looks like we have a no-shoot, sir. Vector 200,
Mission
put it on your
manager.
nose, 8 miles, look for an impact.
Impact at 5855.
When the prized capsule slams into the Utah desert floor, a seismic, emotional shockwave strikes research labs around the world like a forged aluminum Icarus. NASA's flight to the sun has ended in tragedy. The SRC is in pieces, the sample capsule is breached, and the most carefully protected unmanned payload in NASA's entire history lies in a sunken crater of dugway dirt. Dirt that's been exposed to 60 years of chemical and biological weapons testing. The recovery team is not allowed near the capsule because of toxic gases from the SRC's batteries and the unfired drogue chute explosives. As they wait for access, questions fill the air. What went wrong? And how bad is it? And what about the solar wind ions buried deep in the pure element collectors? After the gases dissipate and the explosive charges are disarmed, the NASA recovery team goes to work to recover even the tiniest of fragments of the collector arrays. The arrays and solar collectors, in 15,000 pieces, are carried with the buckets of debris and desert sand to an impromptu clean room. Scientists begin the painstaking process of separating the shattered arrays from sand and other wreckage, with the ultimate goal of determining if contamination has destroyed all scientific value in these priceless pieces of the ancient past. Meanwhile, NASA investigators want answers. How could a $100 million mission end in a devastating crash landing? The investigators focus their attention on the failure of the drogue chute. NASA has used parachute re-entry systems in one form or another since the very beginnings of the space program. It is regarded as a heritage system, and it always works. Well, almost always. When the capsule leaves the vacuum of space and hits the density of Earth's atmosphere, a switch called a gravity switch, or G-switch, is thrown forward, sending an electronic signal to 4 explosive charges that blast away a cover plate to deploy the drogue chute. Just like when driving a car and hitting the brakes, anything not secured will be thrown forward. The gravity switch works on the same principle. The force of the atmosphere meeting the momentum of the spacecraft and throwing the switch forward. The switch starts the automated landing sequence. There are very few ways it can fail because it is not computer or electronically activated. It is a rocker switch that simply rocks forward when the spacecraft hits the atmosphere. Genesis was equipped with 4 gravity switches, 2 primary and 2 backup switches, installed in case the 2 primary switches fail. Investigators recover both the primary and the backup gravity switches from the wreckage and find them perfectly intact and not activated. While scientists work tirelessly to salvage the solar wind ions, NASA is about to discover the shocking cause of the crash, the end of Genesis. With the Genesis capsule wrecked, and scientists trying desperately to determine what, if any, scientific material will survive, the crash investigators review the spacecraft's design plans and engineering paperwork. Everything appears in order. The paperwork indicates the gravity switches were installed properly, along with the drogue chute and parafoil. While frustration with the investigation builds, a small ray of hope begins to emerge from the science recovery team. Some of the collectors are still intact, and the pure element wafers appear to have done their job. Many of the long-sought ancient ions remain pristine and uncontaminated.
One of the collectors is a piece of gold foil. Think very, very thin aluminum foil, but it's gold instead, and so it's even more fragile. It was completely intact, not damaged at all.
While the scientists were feeling optimistic, the crash investigators were not. Then, an X-ray examination of the switches finally provides a breakthrough. The primary switches are backwards, and the backups, they are backward too. As the sample-return capsule entered the atmosphere at over 27,000 miles per hour, the dense atmosphere began resisting the spacecraft, which should have thrown the switch forward. But because it was installed backwards, the switch did not move. It could not be thrown into a forward position because it had been installed in the forward position. The drogue chute never deployed, causing the capsule to tumble out of control. So when the spacecraft hit the brakes, the switch was already forward and didn't move. Once again, human error had proven disastrous. A wide-ranging investigation revealed that another program's engineers had made some design changes to the avionics unit which shifted the circuit boards and the gravity switches installed on them. A standard centrifuge test would have caught the problem, but the test was not performed because the Genesis avionics unit was delivered 4 months late for testing, and because the gravity switch was considered a heritage system that was approved without the test. But NASA concluded that the design changes should have required the additional testing. NASA learned from the mistake and implemented rigorous reviews and evaluations of all mission-critical systems for every mission, and issued notice that just because a system has a backup, it still must be checked as reliably as all other systems. The spectacular crash landing of the $100 million Genesis sample return capsule demonstrates the risks of human error to space exploration. But human ingenuity, resilience, and a lot of hard work ultimately salvaged the science. NASA declared that all the mission's primary objectives were achieved, and groundbreaking research continues to be conducted on recovered solar wind ions. Studies on oxygen and nitrogen isotopes, as well as neon and argon isotopes, have confirmed some solar theories and revealed surprising levels of oxygen in the sun. Research continues.
Just because we can't analyze something today, and most of what we're getting back we can analyze, wait 5 years.
As humans continue to reach for the stars, driven by the spirit of exploration and the joy of discovery, human error is always a possibility. But human determination will always find a way to fix the problem, to go further and discover more.
Landing gear down and locked. Having fired the imagination of a generation, a ship like no other, its place in history secured, the space shuttle pulls into port for the last time. Its voyage at an end.
The space shuttle program ended in 2011 after 133 successful missions.
Mission complete, Houston. After serving the world for over 30 years, the space shuttle has earned its place in history and has come to a final stop.
When the first space shuttle launched in 1981, the program was the most groundbreaking, ambitious space exploration effort in human history. The science fiction concept of regular treks to and from space had suddenly become reality. At the height of the program, the space shuttles were flying 3 to 8 missions per year, constructing the International Space Station, maintaining orbital telescopes like Hubble, and enabling groundbreaking scientific research and discoveries that changed the way humans lived on Earth. But with literally millions of parts to this amazing flying machine, and a labor force of up to 7,000, the scope and complexity of America's space transportation system made mistakes almost inevitable. There were simply too many people and too many variables to expect nothing would go wrong, and on occasion, it did. Most space mistakes are caused by human error, a miscalculation, an oversight, a failure to call for an investigation when something doesn't look right, or even someone trying to do something good not realizing how it affects the entire system. A critical oversight left NASA's solid rocket boosters literally hanging by a thread and put unsuspecting civilians directly in the crosshairs of more than 1 million pounds of the most explosive rocket fuel on the planet. But first, because a material supplier was just trying to help, an astronaut's life is put in danger during a harrowing training exercise. The orbiter is the part of the full space shuttle that operates in space and returns to Earth. It is equipped with what is called an emergency egress slide. The slide is similar to the escape slides used on commercial aircraft, which have saved many lives. The orbiter's egress slide could be used in a transoceanic abort landing, a scenario which would force the shuttle launch to be aborted and the orbiter to land in the ocean, a critically dangerous scenario that would only play out if something went horribly wrong during launch. The slide could also be used in an emergency landing situation when the orbiter returns from space. During entry, descent, and landing, or EDL, the orbiter becomes a glider, The entire 5,000-mile flight through the atmosphere, starting at supersonic speeds of 17,000 miles per hour, is unpowered, with only restricted directional control available to the pilot. A series of banking maneuvers along with atmospheric resistance are used to slow the orbiter as it approaches for landing. With no engines, the orbiter has no ability to make a second landing attempt if something goes wrong. It cannot circle around for another attempt like a typical airplane. It has one chance to get it right. An obstruction on the runway or a mistimed or misaligned approach could result in the orbiter landing in a Florida swamp. The emergency egress slide was designed for just such a scenario. Although the slide was never needed during the history of the Space Shuttle program, learning to deploy and use the slide was a critical part of each astronaut's training regime. One training exercise went terribly wrong. Astronauts are assigned to missions based on experience or expertise in science or spaceflight, depending on mission objectives. Training for an assigned mission can take up to 3 months, while planning for that mission can take years. Astronauts' lives and health are tightly controlled during the intensive training phase. As launch day approaches, if an astronaut becomes injured or gets ill, the entire mission can be delayed, which can cost millions of dollars, and in some cases, narrow windows of success can be lost, such as repair missions to the Hubble Space Telescope. So once training begins, astronauts are closely monitored and protected. While training with the emergency escape slide, astronauts wear full flight suits, and before they can be cleared for launch, they must be able to fully deploy the slide and exit the orbiter in under 7 minutes.
Atlantis Houston, MS3 ComCheck. Tab release. Visor.
As they descend the rubber inflatable slide, a carefully calibrated strip of coarse material slows the astronauts so they are not injured by descending too fast. This strip is called the deceleration strip. A decorated female commander and 2 other male crew members were training for an upcoming mission. The first 2 crew members exited the vehicle and noticed that their descent was slower than usual. But in the urgency of the training exercise, there was no time to stop the commander from descending the slide. And when she did, her mission and NASA career almost came to a tragic end. A routine training mission quickly turns into a life-threatening situation as astronauts practice deployment and use of the orbiter's emergency egress slide. After deployment of the slide, heavier crew members notice their descent is slower than normal. When the lightest crew member descends, she stops suddenly when she makes contact with the slide's deceleration strip. The sudden stop causes her to lose balance, and she nearly tumbles down the slide. Such a tumble in a full flight suit could have resulted in life-threatening injury. This also could have seriously delayed the mission, costing millions of dollars. The astronaut is carefully assisted off the slide. Training exercises are suspended, and an investigation is immediately launched. The deceleration strip is analyzed. Testing reveals that the material is 3 times coarser than it is supposed to be.
During the development of the requirements to procure this particular item, there is an expectation that those products will be delivered to us as we expect them to be.
In disbelief, NASA contacts the supplier of the slides, and a grave concern emerges. Are the slides currently installed in the actual orbiters wrong as well?
We design and we train and we provide equipment that is destined to go into the harshest environments of space. And our first priority on this is to make sure it's done safely.
Is the health and safety of the astronauts in jeopardy from the very device designed to protect them? NASA needed answers, and fast. The investigation confirms that NASA had ordered 6 new egress slides to replace slides that had been in operation for 10 years.
When we're procuring an item from industry, we go into extreme details on creating the contract. And within the contract to this vendor, requirements are established, processes are established, and the criticality of the product is communicated to the contractor.
The slide with the wrong deceleration strip was one of the new slides, and two of the other new slides had already been installed in Columbia and Endeavor. While talking with the primary company that manufactures the slide, NASA discovers that a second company that supplied the rubber-coated nylon deceleration strip also supplies the same material to a military customer. The material is used in a classified military application to evacuate troops from an area quickly. The military customer, who bought much more of the material than NASA, asked the company to make the material rougher to help soldiers evacuate easier. They changed the material but failed to modify the material part number. When the Space Shuttle program ordered new slides, the new, rougher material was provided for the deceleration strips. The primary company that puts the slide together checked the part number, but did not test the deceleration strip when it was delivered. They assumed the material was correct based on the part number. The slide was assembled and delivered to NASA.
Any deviation or any change of those processes need to be communicated back to the customer. And whether the company thought it was insignificant or not, based upon how we're using this material, it should have been communicated back to us.
The company that supplied the deceleration strip material thought that changing the material was a good thing to protect the lives of United States troops. But because the change was not reported to NASA, it jeopardized the life and health of an astronaut and a space shuttle mission.
Processes are established for one result, and that is a safe and successful mission.
Fortunately, the deceleration strips were all replaced with little effect on mission schedules. As NASA builds the next generation of spacecraft and sets its sights on Mars, the space agency is working to ensure this kind of space mistake never happens again.
Process is a process no matter which program is being worked on, and the change impacts still have to be understood and analyzed so that we can pass on from one program to another, because ultimately we're all going to space.
Next, a critical oversight leaves NASA's solid rocket boosters hanging by a thread, a costly space mistake that put unsuspecting civilians directly in the crosshairs of more than 1 million pounds of the most explosive rocket fuel on the planet. NASA learns from their mistakes.
Houston, we've had a problem.
And NASA works hard to catch mistakes before it's too late. Space Shuttle program lessons are still being applied to today's new spacecraft. The Space Shuttle was comprised of 4 primary components. The orbiter, where the Space Shuttle is piloted and from which the astronauts live and work. The Space Shuttle main engines, or SSME, which are housed in the aft section of the orbiter and provide directional control during launch and descent. The external tank, which supplies the liquid hydrogen and liquid oxygen to the Space Shuttle main engines. Finally, the solid rocket boosters, or SRBs. The SRBs together provide the 6 million pounds of thrust needed to launch the Space Shuttle and escape Earth's gravity. The SRBs arrive at Kennedy Space Center in 4 sections, each weighing 325,000 pounds. The sections are transported from Utah across the nation by rail. The very earliest rockets were solid fuel rockets powered by gunpowder. Invented by the Chinese in the 13th century, they became weapons of war for the Chinese, Indians, Mongols, and Persians. Intercontinental ballistic missiles, like America's Minuteman and Peacekeeper, Russia's Topol, China's Dongfeng, and India's Agni 5, all utilize solid fuel because they can be stored for long periods of time and can launch on short notice. When the Space Shuttle launches, the Space Shuttle main engines are activated first. Then the SRBs are ignited. Once ignited, they cannot be turned off or stopped. Within seconds, the shuttle clears the launch pad. The power of the SRBs force the Space Shuttle through the resistance of the atmosphere and out of the grasp of gravity. As it ascends, the Space Shuttle travels faster and faster while gravity becomes less and less. The SRBs have a short but powerful life. They burn out and are jettisoned just 2 minutes after liftoff. The Space Shuttle main engines spend the remainder of liquid fuel from the external tank to reach orbit. The spent SRBs plunge harmlessly into the Atlantic Ocean, some 150 miles downrange. Days before launch, NASA dispatches 2 retrieval ships, 1 for each booster. The ships wait in a safety zone near the projected splashdown location.
There it is. Straight out.
They retrieve the spent boosters. And tow them back to Kennedy Space Center. The booster casings will be refurbished and used again. When the solid rocket booster's 6 million pounds of power is controlled and directed to reaching orbit, it is an incredible feat of human engineering. The Challenger disaster of 1986 is a painful reminder of the violence and destruction that happens when that power becomes uncontrolled. A seal between two rocket motor segments was damaged by ice before launch. 73 seconds into flight, gas from the burning solid fuel erupted through the seal.
Challenger, go at throttle up. Challenger, go at throttle up.
One minute, 15 seconds. Velocity 2,900 feet per second. Altitude 9 nautical miles. Downrange distance 7 nautical miles.
And within seconds, the entire rocket was torn apart. The first explosion initiated a series of events that led to the explosion of the liquid fuels in the external tank. None of the crew survived.
Flight controllers here looking very carefully at the situation. Obviously a major malfunction.
Due in part to the volatile nature of solid rocket fuels, the Space Shuttle's SRBs were manufactured and refurbished at an isolated facility in the deserts of northern Utah. The facility is just miles away from the Golden Spike National Monument, where the East and West were joined by the Transcontinental Railroad in 1869. The final Golden Spike linked the United States together. Trains were the new technology of the day and were transforming the world, opening new commercial opportunities and the freedom to travel coast to coast. Golden Spike is a fitting location for manufacturing the rockets that today, like the trains of old, are opening up new commercial opportunities in space and will usher in an era where space travel is commonplace for would-be explorers. When the SRBs return, the casings and nozzles are cleaned, then insulated with a protective carbon-carbon material. The solid rocket fuel is created, and the boosters are reloaded. Occasionally, a fully loaded SRB would be fired to test design improvements or modification. The powerful rocket is secured horizontally and fired.
1, fire.
Several feet of sand is placed on the ground behind the rocket to protect the test stand. The blast is so hot that the sand is liquefied, and when it cools, it turns to glass. The temperature of the flame as it exits the nozzle is 5,600 degrees Fahrenheit, the same temperature as the sun's photosphere, the visible layer of the sun. When the rocket segments are fully loaded with fuel and ready to ship, NASA's mantra is, handle with care. An accident with a fully loaded rocket segment could be devastating. The SRBs are transported to Kennedy Space Center in Florida by rail from Utah. The trip is over 3,000 miles, taking the explosive rocket segments through or near numerous populated areas across the United States. After they arrive at KSC, the segments are joined together in the iconic Vehicle Assembly Building, or VAB, then mated to the external tank, which is attached to the orbiter, and the space shuttle is ready to launch. Just southwest of the VAB is NASA's Locomotive Maintenance Facility. Frequent maintenance and repair is performed to keep the mission-critical NASA train fleet in top condition. Chris Bryant takes care of the rail cars.
Our main job is to maintain all the rolling stock as far as the cars, locomotives, anything to do with the railroad. That's what our job is.
While Chris was working to replace a worn-out brake hose, he discovered a hidden problem that would forever change how NASA handles solid rocket motors.
The day that we were working, our job was to do the hoses. That was required, and that's what we were doing. I was underneath hooking the hose, and it so happened to be where the center plate is. And my job by trade is a welder. So I'm always looking for cracks or anything, just something out of the ordinary. Just happened to look up and seen the crack. When I did, I reported it to my lead. At that point, we stopped everything. They knew that it was bad. I think it was out of about 63 or 64 inches of circumference of the weld, About 61 inches was busted.
The center plate was hanging by a thread.
The magnitude of the crack was that of the 360 degrees around the center plate, the crack was 340 degrees. So there wasn't much holding it there.
The center plate is the main bearing point, contact point between the railroad car body and the trucks, the part that they actually roll on. There is no other feature. There's no redundancy in its safety. And by that single point failure, it was just a matter of time before they separated.
You would lose the solid rocket motor on a derail incident. Extremely concerning to the program.
NASA immediately stopped all trains and launched an emergency investigation.
The response was very quick. We had a lot of attention. They flew a bunch of people in, Alabama and the Marshall Flight Center, Houston. They had a lot of people here.
NASA awarded Chris for discovering the issue, but what he did not realize at the time is that he may have prevented one of the biggest disasters in NASA history. A broken weld puts a stop to all NASA trains.
We jacked up the cars and disassembled them so that everything that was involved could be inspected and x-rayed, and because first you had to determine what caused the problem before you could make a repair that was going to be worthwhile.
An investigation team simultaneously begins searching for the cause while inspecting all the rail cars in the fleet, hoping the issue is isolated to this one rail car. It was not.
We use 200-ton rail cars to move the segments. We have 24 of these cars in our fleet.
NASA is shocked to discover that out of the 24 rail cars, 22 had damaged welds. For years, the rail cars had been carrying fully loaded rocket segments across the United States. If any one of the 22 damaged welds had separated all the way, the resulting accident would have been catastrophic.
When they're underway, each car is close to 500,000 pounds each, and if you're moving at 50 miles an hour, that 500,000 pounds will travel quite a ways before it comes to a stop. So it could end up being a pretty good mess.
Extensive analysis and computer modeling was conducted to determine why the welds were breaking and why the problem had not been seen before. The same rail cars had been used since the beginning of the Space Shuttle program. For 20 years, the massive weight of the SRB segments created tremendous stress and strain on the center plate. Over years of use, the weld holding the center plate to the flatbed began to break, eventually leaving the volatile rocket segment hanging by a sliver of metal. If the final inch had broken, the center plate would have broken loose, the flatbed could have collapsed on the wheels, derailing the entire train and sending the fully loaded rocket segments tumbling out of control. The moment the fuel encountered an ignition source like fire or sparks, an unstoppable and uncontrollable chain reaction would begin, destroying the SRBs and everything around them. On their trip from Utah, the trains traveled through both small and large towns. Had the weld completely failed in a populated area, an uncontrollable fire and explosions could have caused widespread damage to buildings and homes, and possibly loss of life. The fuel is highly toxic as well, which would have required large-scale evacuations. According to the Federal Railroad Administration Office of Safety, there are approximately 850 train derailments each year. Many are minor, but some wreak destruction in their paths. Rail is still considered one of the safest and most cost-effective ways to transport goods across long distances. But when something goes wrong, the results can be devastating. The last tiny inch of the weld holding the center plate in place and one technician's timely discovery had prevented a possible program-ending accident that could have been second only to the loss of Columbia and Challenger. With the entire NASA train system shut down, new solid rocket boosters are now stranded in Utah. But an aggressive launch schedule is demanding a constant fresh supply of the rockets. If NASA cannot fix the problem soon, millions of dollars would be lost in mission delays. This space mistake is a chilling reminder that the dangers of space exploration are not only restricted to launches, landings, and on-orbit mission objectives. The manufacturing, transport, and processing of the highly explosive fuels and motors, which in many ways are the heart of space exploration, are just as critical. For over 20 years, the rail cars were used to transport the rocket segments, but the center plate had never been inspected in all those years.
Years ago when these cars were built, we used different standards for our safety factors and stuff. And these cars being very heavy caused fatigue. The acceleration of the fatigue was more than anticipated. And it should have been caught sooner, but using the old guidelines, they were within the normal range of the old guidelines, but we just found out that our inspections have to be more frequent and a little bit more intense.
NASA initiated an aggressive repair schedule to fix the broken wells. To reduce the strain on the center plate and slow down the degradation of the wells, NASA lowered the speed limit of the trains transporting fully loaded segments. NASA also implemented regular inspections of the wells, solutions that will all lead to the flight schedule being met and a successful controlled process of transporting the segments.
We need to have a good inspection criteria. We need to have a good repair criteria. And once that's established, which we believe we have, we need to make certain that we don't drift from that.
Today, solid rocket motors for the new generation of spacecraft are still being shipped from Utah and other places across the country by rail. NASA learned from their mistake and fixed the problem. Each previous generation of spacecraft provides a wealth of knowledge and experience to further exploration. As NASA focuses on placing humans on Mars, new challenges await. Many improvements will not even be discovered until something goes wrong, because space exploration is fueled by the unknown. No one can fully predict how the harsh environment of Mars may affect people or hardware, which is one reason we must go there. The astronauts, technicians, and engineers who have dedicated themselves to exploring space will never let mistakes stop them. They innovate, fix the problems, and ultimately become better to go further and discover more. April 12, 1981. Earth's pioneer reusable spacecraft, NASA Space Shuttle Columbia, blasts out of the Kennedy Space Center to the cheers of millions worldwide on its first mission into space. 22 years later, on January 16, 2003, Columbia blasts off on its 35th mission.
Roger, roll, Columbia.
Shuttle in a heads-down, wings level position for the 8.5-minute ride to orbit.
As the mission enters its 16th and final day on orbit, 80 experiments have been completed in fluid physics, material science, and life science. It has been a successful mission all around, and it's time to return to Earth. Mission Control runs all of its system checks and clearance protocols and examines weather reports to confirm conditions for Columbia's landing.
We are commenting on the cloud cover because all of a sudden this cloud bank had come in and it got very dark and a very low ceiling. So we were commenting, you know, is it going to be okay for them to land? And you know, talking with those folks, they're like, oh, you know, they'll be fine, they'll clear.
And at 8:10 a.m., February 1st, 2003, pilot Willie McCool calmly drops Columbia out of orbit to begin the long glide home. At 8:45 a.m., the external temperature rockets up to 1,600 degrees Celsius, 3,000 degrees Fahrenheit, so routine that the crew shoots a video as they descend. Then suddenly, everything goes wrong. At 8:54 a.m., the crew systems officer in Mission Control announces low readings in the left wing's hydraulic sensors, off the scale low.
Hydraulic return instrumentations.
No, sir, there's not. We've also lost the nose gear down talkback and the right main gear down talkback.
GNC flight.
4 minutes later, the shuttle crosses into Texas from New Mexico at 20 times the speed of sound. 60 seconds later, the low-pressure readings disappear altogether. Capcom reports the signal loss, and Mission Commander Rick Husband clicks his comm button and starts to respond, but never completes Columbia's final radio transmission.
We're also off.
Columbia, Houston, UHF comm check. Columbia, Houston, comm check. Columbia, Houston, UHF comm check.
Pilot's not reporting any RF at this time. GC flight. GC flight. Fly GC. Lock the doors. Copy. Fido, do you have any tracking?
No, sir.
At that time, I heard someone said that we've had loss of signal. I went back up to the NTD to kind of find out what was going on. And at that time, the astronauts had pretty much had just left in a running pace to go back to their vans to go be with the spouses, because at that time we had realized that we had lost the vehicle.
Shortly after 9 a.m., February 1st, 2003, Space Shuttle Columbia breaks apart during re-entry. Columbia and her entire crew are lost.
We had kind of conveyed in the main corridor right out here. And I just said a prayer.
This is real. This wasn't just a bad dream. That was a tough day there. In the past, you know, because of the Challenger incident, we often held our breath when the orbiter was ascending. And of course, when we had SRB separation, everybody took a deep sigh, but we never considered what could happen during re-entry. Or we were hopeful that nothing would happen during re-entry, and now it did.
I have been very good friends with one of the crew members, and I had a discussion with him. And if anything had happened to the orbiter, you know, what should I tell everyone? And so I then, at that time, expressed those words to my coworkers out here, which was, you know, that he holds no animosity for what has happened, and he died doing what he loved.
NASA's response is immediate. Ground all space shuttles, find out what happened, and make sure it never happens again. And do it quickly. The International Space Station and NASA's future depend on it. With the entire program grounded, recovery teams scrambled into the field to gather debris, as satellite data confirms that a hailstorm of evidence has rained down across 2,000 square miles in Texas, Louisiana, and Arkansas. Investigators will have their hands full as Space Shuttle Columbia finally returns to Kennedy Space Center, one piece at a time. Evidence of Columbia's destruction makes its way to Kennedy Space Center. It's delivered to a dedicated hangar where the 84,000 pieces of debris are reassembled, when possible, and laid out on a grid representing the space shuttle.
Initially, because of the high altitude breakup, we weren't that hopeful that we were going to get that much of the orbiter back that would tell us enough information to really help solve the accident.
Less than 40% of Columbia is ultimately recovered, but it's enough for investigators to begin looking for answers. One of the worst tragedies in NASA's history has left the entire space agency with an uncertain future. Grief and confusion combined with a growing concern for the fate of the International Space Station. Just a few miles down the road from the recovery hangar, ISS modules, trusses, and solar arrays are being prepped and ready to fly. It's enough space hardware for 9 shuttle missions. Building the ISS is the #1 priority for the Space Shuttle program. Well, it was before the Columbia disaster. NASA's former chief astronaut and International Space Station Commander Peggy Whitson has spent more time in space than any woman on Earth.
The station would not have been built. The shuttle itself is our truck that brings up a lot of the big cargo. Also brings home a lot of the scientific data, the actual samples that need to come home. We had to decrease the crew size on board the International Space Station in order to just maintain the station. Our focus on board the station changed because we couldn't implement the scientific priorities that we had had in mind for that time period. We couldn't continue the assembly. It was very important at that point in time.
Besides the American components, hardware from 3 international space agencies at a cost of billions of dollars sits on the ground, now with no way to get to space. Everything has been designed especially to fit in the space shuttle's payload bay. There is no other rocket system in the world that can carry the components. Back at the hangar, teams of engineers are assembled to learn what happened, how it happened, and how to make sure it never happens again.
We knew we had to do a recovery or a salvage operation of the debris, and we knew we had to set up to do a reconstruction of the debris based on trying to find all that, gather all that information out of the debris and focus it in an investigation.
Although technical expertise is the key to finding the answers NASA seeks, the team is driven by much more than professional pride.
How do you view a family member? I mean, it's basically the same thing. You spend a lot of your life out here working on an orbiter, and it becomes like a family member to you. A lot of people have spent their whole careers out here working on and around her. And so it hurts.
While the NASA family mourns the loss and celebrates the lives of both the astronauts and the spacecraft, it is not something any of them ever want to experience again. So the search for answers is on, and it's personal.
When you first start seeing the pieces come back, as well as it being an emotional task, it ended up turning to be a very daunting task. For that, you're basically now trying to identify a part by reverse engineering.
The Columbia reconstruction effort was all about receiving the debris from the field recovery sites. It was then taking that debris and identifying it as best we could, laying it out in context with each other so that you could see the parts next to each other, identify the fracture surfaces, the dings, the dents, the burn marks, and try to see what the debris was telling you, to be objective about the debris, to let the debris speak to us, not go in there with any preconceived notions or scenarios and as to how the accident occurred or why the accident occurred. Just let the debris speak for itself.
When the re-entry data recorder is found intact in Texas, investigators hope for more answers.
It's shown that the fatal damage originated between leading edge panels 8 and 9.
The debris is telling, at least from a TPS standpoint, that we had some type of breach between RCC panels 8 and 9. Whatever happened, it wasn't like this big gaping hole and we were missing an RCC panel. Or whatever it was very small. You can see a direct hot air flow that came out from in between the RCC panel and our first row of tiles.
It's the only damage. It's unique in its appearance and in its physical properties. There's almost a complete lack of any metallic hardware. Basically, it's all been melted away. That molten residue has been deposited on the backside of the panels.
And you're going to see distinct flow patterns coming up the sidewall of those particular tiles, heading in an aft direction. For that to get to that state, it has to see temperatures over 3,100 degrees.
When Columbia hit the atmosphere at over 20 times the speed of sound, and the external temperature soared to 3,000 degrees, that breach in the wing allowed superheated plasma to enter the wing, quickly dooming the spacecraft.
The initial reentry, I think, is Mach 24. It's coming in at about a 40-degree angle, so it's kind of coming in like this, and it's basically plowing its way in. The friction of the orbiter hitting the atmosphere will start creating a surface tension called plasma, and the plasma is pulsating glow. At that time, too, that friction also starts the vehicle heating up. Mach 18 is approximately the speed they'll be going over peak heating, which is about 3 miles per second, and that hole allowed airflow to go into that spar area. And I shouldn't say airflow because that makes it sound very passive. It was hot plasma gas.
With the breach confirmed by the physical examination of the wing and the analysis of information on the data recorder, the question remains, what caused it?
Something has to hit it, something has to pierce it, something has to fail.
Part of the investigation team reviews every frame of video from the launch. A piece of insulating foam is filmed breaking off the external fuel tank a minute and a half into liftoff. The foam loss is not a new thing and has become almost routine, but this piece hits Columbia's left wing as the shuttle speeds away from the launch pad.
Debris cloud was almost the length of the elevon, and that really surprised us because we're thinking that that hit had to be very strong and powerful in order to create that type of debris field.
But how could a piece of insulation destroy a space shuttle? The shocking answers will fundamentally change the space industry. And with growing international pressure from International Space Station partners, NASA would have to create a miracle of engineering, and fast. The intense Columbia investigation confirms a breach in the leading edge of the left wing caused the loss of Columbia and her crew. But what caused the damage? After bombarding a reconstructed wing with various sizes of foam at varying speeds, investigators have their shocking answer at last. A piece of foam traveling 530 miles per hour can puncture the wing. It is proven beyond reasonable doubt that the piece of foam that broke off during launch landed the fatal blow to Columbia.
Fundamental root cause was loss of foam debris from the bipod ramp and striking the orbiter and causing damage. As that particle comes off the tank and really is slowed down, and the orbiter essentially runs into the particle.
The investigation's focus turns to the foam. The full space shuttle is comprised of the orbiter, the space shuttle main engines, the solid rocket boosters, and the external tank, or ET. The 154-foot external tank supplies fuel to the space shuttle main engines during launch and ascent. The ET is actually comprised of two fuel tanks. The forward tank, called the LOX tank, contains over 146,000 gallons of liquid oxygen. The rear LH2 tank contains 395,000 gallons of liquid hydrogen. The area between the two tanks is called the intertank and contains most of the electronic components necessary during ascent. The foam insulation is a crucial part of every space shuttle's extensive thermal protection system, or TPS. The spray-on foam is designed to protect the tank from the extreme heat of launch and the extreme cold of the liquid fuels.
The foam is basically there to keep ice frost from forming on the outside of the LOX tank and hydrogen tank, because you can't have ice and frost fall off and hit the orbiter on the way up.
When we're tanking the liquid oxygen and liquid hydrogen, you've got to insulate the metallic tank to make sure that the propellants don't boil off. It's also very influential to densify that propellant. In other words, maximize the amount of thrust that you could get out of that volume of propellant.
There are certain areas where it's thicker, and on the inner tank where you need it for aerothermal protection on ascent from aerothermal environments.
During launch and ascent, extreme aerodynamic heating can create a 1,000-degree difference.
At any one time, you could have within 1 inch of that material about a 600 degree on the outside and about a minus 450 on the inside.
The insulating foam is critical, but why is it coming off? And even more importantly, how can NASA stop it? With the United States Congress demanding answers and billions of dollars of hardware grounded at Kennedy Space Center, NASA is determined to fix the problem and get back to flying. With the International Space Station construction on hold and the shuttle fleet grounded, an extensive investigation places the blame for the destruction of Columbia on foam loss from the external tank. The foam is a critical part of the space shuttle's thermal protection system. There are actually 2 layers of TPS on the external tank. The outer layer is designed to dissipate heat through erosion. It burns away during launch and ascent, taking excess aerodynamic heat with it. But that's not the problem. The problem is the inner layer, the lightweight closed cell spray-on foam that is supposed to stay in place. Since external tanks are never reused, it doesn't matter what happens to the foam after the ET is jettisoned. But until then, it's crucial to the protection of both the LOX tank and the LH2 tank, as well as the intertank. NASA had known for years that the foam insulation was a problem. Small pieces of foam were lost on every flight. They even know why it happened and gave it the name popcorning, because most of the foam loss was small bits that popped off during launch. Not at all like the large suitcase-sized chunk that ultimately destroyed Columbia. The external tank's aluminum lithium surface is painted with a primer and then covered with insulating foam. When the foam is sprayed onto the ET, random tiny air pockets form, which can weaken the bond between the painted aluminum alloy skin of the ET and the foam. The issue becomes a problem when the inner tank is purged with nitrogen to decontaminate it and to remove moisture just before launch. In the cryogenic temperatures created by the LOX and hydrogen fuel, the nitrogen liquefies. The liquid nitrogen then can flow through the intertank flange into the empty pockets created during the foam application. Other voids are just filled with air. The air liquefies similar to the nitrogen. When the shuttle heats up during launch and ascent, the liquids turn back to gas and expand, which makes small pieces of the foam pop off.
What we found in there were a lot of defect inclusions that we were surprised to see. We didn't realize some of those inclusions could be rather large
large enough to shear a suitcase-sized piece of insulation completely off the external tank and send it careening into Columbia's wing. Ignored and accepted for years, foam loss had simply grown worse, especially in the areas of the ET that weren't smooth, like the left bipod ramp that holds the external tank to the orbiter, the source of the breakaway foam that took down Columbia. NASA learns from their mistakes as the world watches and wonders if the space shuttle will ever fly again. One simple solution is about to make history. NASA determines that pockets of air in the external tank's foam insulation are responsible for the tragic loss of Columbia and her crew. With a $100 billion International Space Station only about 30% complete, research organizations around the world have placed scheduled zero-gravity studies on hold.
We are pre-positioning a lot of hardware and supplies. It is the only orbiting laboratory in the world, and it gives us a capability to do experiments on in a long-duration platform that nothing else has ever provided us before.
Their logistic modules and laboratories are useless until the space shuttle can fly again.
We put together a series of teams that looked at all applications of thermal protection systems on the external tank and highlighted the areas that were of highest concern to us. And we went through a process with the program of evaluating each of those areas and determining which ones we felt like had to be addressed for return to flight.
One of the issues that we saw in the investigation of the accident was that the design that we're putting onto the tank was not what we thought it was. In other words, there were some defects in the material that we could not see through NDE or any kind of inspection technique.
The bipod ramp became a central focus because it was the source of the foam that hit Columbia's wing and the most likely place for the problem to occur again. A simple fix that took some ingenious engineering fixed the problem. The bipod foam was replaced with heaters.
What we determined is that we could replace that whole large foam with heaters mounted at the base of the bipod. That could prevent ice formation. They only are active prior to launch, and then we shut them off before we launch. So in that regard, we were able to get rid of the larger piece of foam.
The foam application process was also a major issue.
What we're trying to do with the foam now and the foam flows that we have now is eliminate or minimize the size and the number of defects that we get when we're spraying the foam.
Now we know that defects on the inside have a big influence on the material performance. Therefore, the way that the material is laid down onto the tank is very important. Previously, those techniques were left fairly open to the liberty of the technician to apply.
Being a manual operation, we wanted to standardize how they did that, just not say go spray foam. Give them some sequences and techniques that we would prove through a series of development enhancement and verification activities to show that it would work and it was repeatable is what we were trying to do.
NASA standardized the spray techniques and implemented other safeguards as well. Video recordings of all sprays, a second technician to assure quality, constant monitoring of the foam for consistency, and a more vigorous certification process for technicians. In addition to fixing the external tank issues, NASA also launched a fleet-wide recertification program for all the other space shuttle components, the orbiter, solid rocket boosters, and space shuttle main engines. The work took 2.5 years. 7 space shuttle missions had been postponed, and the International Space Station was years behind schedule. Finally, on July 26, 2005, Discovery and her crew were set to return to space. NASA hung their hope on all they had learned. Would it be enough? The launch is a success. Discovery spent 13 days and 21 hours in space. Along with resupplying the International Space Station, their primary mission was flight safety evaluation and testing, and Discovery and her crew came home. Ultimately, the $100 billion International Space Station was completed and stands as one of the greatest construction projects in human history.
The international cooperation, I think, provides something that we will look back on later and say, hey, that was the first really big peacetime project that so many countries pulled together and completed.
Along with providing a platform for scientific advancement and discovery, the ISS symbolizes global cooperation and demonstrates what is possible when the best of humanity comes together. The Space Shuttle program ended with the final flight of Atlantis in 2011, after 30 years of building, improving, and learning how to operate in the great beyond.
0 and liftoff, the final liftoff of Atlantis on the shoulders of the Space Shuttle. America will continue the dream.
Roger, roll, Atlantis.
Houston now controlling the flight of Atlantis. The Space Shuttle spreads its wings one final time for the start of a sentimental journey into history.
Today, NASA is using all the knowledge it acquired over those 3 decades to venture past Earth's orbit to Mars, where the new Orion spacecraft will land the next generation of the courageous family of space explorers.
It obviously isn't an easy thing to transition to a new program, a new vehicle. I hope that we will be as successful in transitioning, if not more so, but it's important that we try.
Explorers who are driven by the spirit of discovery, and even when faced with the worst tragedies, innovate, fix the problems, and ultimately become better. To go further and discover more.